So now what we want to do in this chapter is talk about how multimedia information such as colors and like you have in a picture or in video are represented digitally in the computer, as well as sound information that can be recorded and stored digitally and then reproduced through speakers from your computer. So let's start with color information. If you recall, the computer screen is a matrix of rows and columns, and the intersection of these rows and columns is called a pixel, for standing for a picture element. And what the computer does is it controls the amount of light intensity in the spectrum of red, green, and blue inside each of the cells, and the collection of the cells create a sort of mosaic that forms a picture on the computer screen. So each value of red, green, and blue light for a cell is represented by an 8-bit byte. So altogether you have 24 bits that represent the color inside any one pixel element on the screen. When the smallest value that we can express in an 8-bit binary number is used for the amount of red, green, and blue, we end up with a value or a color of black. So if we have 0, 0, 0, 0, 0, 8 zeros for the amount of red, the amount of green, and the amount of blue, we have the color black. When we're at the other end of the spectrum and we use ones in each of the locations of the 8 bits for the color red, the color green, and the color blue, which is also represented as a value of 255 in decimal, then we get the color white in the pixel. All right, so those are the two ends of the spectrum with respect to the binary numbers that can be represented for red, green, and blue. So in this kind of situation, we have a bit pattern that is neither 0 or all ones. And the bit pattern, though, is repeated for the amount of red, the amount of green, and the amount of blue. It's the same bit pattern. And so the question might be, what does this color represent? Well, first of all, let's do a quick conversion of the number from binary into decimal. And again, if you remember, this is the ones place, the 2, the 4, the 8, 16, 32, 64, and 128. So we have 128 plus 64 is 96 plus 8 is, it's 192. 128 plus 64 is 192, plus 8 is 200. So this value, this binary pattern represents 200 in the amount of red, green, and blue in a given pixel. And that gives us a medium gray. Whenever you have numbers between 0 and 255, and all red, green, and blue values are equal, you'll have this level of gray, in this case close to 255, the maximum, which would be white. So 200 is sort of a medium gray color. So let's investigate how the computer actually can manipulate the bit pattern in order to get, in this case, a lighter colored gray. What we'll do is we'll take the bit pattern we just looked at, which is representing 200, and then take a bit pattern that represents the number 16 in decimal, and then add them together, and this is the bit pattern of 216. So now we have 216 as the amount of red, the amount of green, and the amount of blue, and that gives us a lighter colored gray, closer to white. So we need to see how the computer does this binary addition. And it works similarly to the decimal addition, but reflects a base 2 numbering system. Like decimal, binary addition works from the right to the left, and in some cases we have digits that can be added together, such as 1 plus 0, and it can be represented as a single binary digit, in this case 1. Or we might have had them backwards. 0 plus 1 is also equal to 1, or 0 plus 0 is equal to 0. In other cases, we have a problem with representing the data with a single binary digit. So, for example, 1 plus 1 is a binary value 2, which has to be represented by 2 bits, 1, 0. So a 2, if you remember, this is the zeros place, this is the one, this is the ones place, this is the twos place. In order to represent a 2, we have to have 2 binary digits. So what we end up doing in the binary addition process is we put down a 0 and we carry a 1 over to the next column, much again like you do with decimal. So let's see how this works. Take an example. We have the binary pattern 110 and the binary pattern 1010. And we're going to add, after we've lined them up from right to left, we're going to add each column. So here we do a 0 plus a 0 equals 0. And then we have a 0 plus a 1 equals 1. We have a 1 plus a 0 equals 1. And a 1 plus a 1 equals 0, carry a 1 to the next column. So this is the bit pattern that we have after we've added the 2 binary numbers A and B together. Now let's just do a quick conversion from binary to decimal so that we can verify what we have here. Again, this is the 1, 2, 4, and 8's place. So number A is equivalent to a decimal 8 plus a decimal 4, right, which gives you a decimal 12. And then B is a decimal 8 plus a decimal 2, which gives us 10. And so adding those together, we get 22 decimal. So let's check over here to see what we have. So this is the 1, 2, 4, 8, and 16's place. So we have a 16 plus we have a 4 plus a 2. And that would be 22. So you can see that the binary addition is actually correct. We've checked it by converting each of the 2 binary numbers being added together into decimal in order to double check our math. Let's try another one. So we have the binary number A, which is 01011, the binary number B, which is 00111, and let's go through the process again, right to left, of adding these numbers. So a 1 plus a 1 is a 0, carry the 1. A 1 plus a 1 plus a 1 is a 1, carry the 1 to the next column. A 1 plus a 0 plus a 1 is a 0 with a 1, carry. A 1 plus a 1 is a 0 with a 1, carry. And a 1 plus a 0 plus a 0 is just 1. So we end up with this bit pattern after we do the binary addition of A and B. So again, let's check real quickly to see what we have here. We have an 8 plus a 2 plus 1 for an 11 as A. And then we have a 4 plus a 2 plus a 1, equivalent of 7. And we get 18 out of this then. Let's double check over here for our binary sum to see what we've got. We've got 16 and we have 2. And again, that is going to be equal to 18. So we've checked our math, and the binary addition that we've done here is correct. Let's do one last one. So we're going to add 1 plus 1. That's a 0, carry a 1. 1 plus 0 plus 1. That's 1 plus 1. That's a 0, carry a 1. 1 plus 0 plus 0. That's the same as 1 plus 0. It's a 1. No carry. 1 plus 0 is a 1, no carry. 0 plus 0 is 0, no carry. 1 plus 1 is 0 with a 1 carry, and then 1 plus 1 plus 1 is a 1 with a 1 carry into the next column. And this would be the pattern then that we end up with after we add A and B together. One more time, let's double check on our math to see what we've got here. This is the 1, 2, 4, 8, 16, 32, and 64 column. So we have a 64 plus a 32 plus an 8 plus 1. All right. So 64 and 32 are 96. Plus 8 is 104. Plus 1 is 105. So this bit pattern is 105. A is 105. And then we have 64 plus 32 plus a 2 plus a 1, and again that's 96 plus 2 is 98 plus 1 is 99. We add these together, that is 14, carry the 1, that's 10, carry the 1, that's 204 decimal. That's what we should have then when we decode this, which is 128. That's what this bit represents. Plus we have 64. Plus we have 8. Plus 4. 128 plus 64 is 192, plus 8 is 200, plus 4 is 204. So we've confirmed that the math here that we've done in binary is correct by converting each of the binary numbers into decimal so that we could check them. So in some cases, computers have fixed byte sequences in terms of their size, and when we carry a bit into the column that is not represented within that fixed size bit sequence, we have a condition called overflow. And overflow exceptions are things that computer programmers have to deal with in order to recover from errors.